So we discussed this example a bit the other day, but let me refresh your memory on this. What we were looking at was the cost of joining LA Fitness and being a member for however long. There was two different programs that they had. One cost $55 per month, so 55x plus 250 to start up. X is the number of months that you're enrolled. Or the other possibility is $45 per month plus 350 to sign up. If you looked at these two equations, then the top one would have to be this one because it has a bigger y-intercept. So that's y equals 45x plus 350. And the other one is 55x plus 250. And you can see that the bottom of these two equations has a steeper slope. It's rising faster. And at some point, these two lines cross each other. And that's kind of the break-even point. That's where it costs just as much to join at $250 a month and pay $55 a month as it does to join for $350 and pay $45 a month. So that's your break-even point. If you were going to join and be a member for 9 months, you'd probably want to join at this program. 10 months or greater, probably on this program. So the point of this problem, though, is to introduce systems of equations. And this is a system of equations right here. You're looking for the solution of two equations and two unknowns. We're going to find where these two lines cross each other in different ways. But let me introduce some vocabulary regarding this kind of stuff. When you have a system of equations that's consistent, that means the system of equations has a solution. So it means that these two lines actually cross each other at least at one point. So this first system of equations drawn here is consistent. Now the other piece of vocabulary that we use to describe this is in whether or not a system is dependent or independent. A dependent system of equations really means that the two equations are the same line. Well, are these two equations graphed by the same line? No. So if you're not dependent, what are you? Independent. Independent. So this is a nice, consistent system of equations. Consistent, independent. That's what we like to see from our system of equations. We're not always going to be so lucky to see that, but that's what we like to see. By the way, can anyone estimate the solution? Where do these two lines cross each other? Take a look at the graph. All right, so 10 and I'd say 800. That's your solution. That's what we're looking for, not only in this section, but in this chapter, is where those two lines cross each other. And it's something you're going to go back to time and time again, but that's your solution, is where two lines cross each other. Now, on your exam that you just got back, one of the ways you could have earned extra credit was to show that something was a solution to an equation. We're going to take that a little bit of a step further. We're going to look at problem number 14 and decide if something is a solution to a system of equations. So problem number 14 gives you 2x plus y equals 5 and 3x minus y equals 0. They want us to decide whether or not the point 1, 3 is a solution. Let's understand what it means to be a solution. If it's a solution, then this point with coordinates for x and y satisfies both equations. Is that true? Well, let's find out. Let's plug it into the first equation. 2 times 1 plus 3. Does that equal 5? Yes. But I have to substitute into both equations. So let's see what happens when I substitute in the other equation. 3 times 1 minus 3. Does that equal 0? That's true. So 1, 3 is a solution to the system of equations. That's what we're looking for. In fact, let's go one even better. Let's do kind of a visual on this. I'm going to use some graphing software to graph both of these equations. Do you think I'm going to see these two equations cross each other? Let's find out. So let me shut these off. And let's graph 2x plus y equals 5. Do you remember the website that I used for this? Desmos. Good job. There we go. And then 3x minus y equals 0. And look, right there. The point 1, 3, that's where the graphs cross each other. This is a consistent, independent system of equations. And there's your solution. Of course, all we really had to do is verify that the point 1, 3 was a solution. I don't suggest you do it by graphing necessarily. We can. We will. In fact, that's what we're going to do with problem number 28 coming up, is take a look at this by graphing it. So in problem 28, we've got two equations. X plus y equals 4 and x minus y equals negative 2. I want to graph both of these equations and see if and where they intersect. So let's work on graphing that. Well, maybe the easiest thing to do would be to draw a t-table. And especially for the first one, that's not going to be so hard. What values can I plug in here to get values of x and y that satisfy the equation? I'd plug in x equals 0 and y equals 0. Those are the easiest points that we're going to get. So Roy, if x equals 0, what does y equal? And if y equals 0, x equals 4. So some nice symmetry there. Let's plot those points. So that's 0 and 4 up here, and 4 and 0 down here. We play connect the dots. And we get a line that looks like this. Okay. I'm going to help out a little bit with the next one because the graph is not quite perfect, not quite big enough to fit here. As with the previous one, we could say y equal to 0 and x equal to 0. So let's start by setting x equal to 0. If I set x equal to 0, I get 0 minus y equals negative 2, which is basically negative y equals negative 2. How do you solve for x? Or how do you solve for y? What do you have to do? Divide by negative 1. So what does y equal? 2. So 0, 2. That's 1 point. Okay. 0, 2 is right here. I need another point. You can set x equal to 0. I mean, that's a typical, or I mean, set y equals 0. That's a typical reaction. It's just going to mean we're going to need to add a little bit to our graph. That's all. So if y equals 0, what do I get for x? Negative 2. So you just have to make your graph a little bit bigger and draw in a negative 2 there. So I'll put a point here on the x-axis. And then let's play connect the dots. There. Now keep in mind what we're looking for when we're trying to work with this system of equations. We're trying to see if these two lines cross each other. Well, they clearly cross each other. So where they cross each other is the solution. What's the solution to this system of equations? McKenna? Yeah, 1 and 3. So 1 and 3. Cool. That's your solution. Eventually, in sections 4.2 and 4.3, we're not really going to be looking at the graph anymore. But it's really in your best interest to keep in mind what's going on or what could go on. The geometry that you see here. And what we're seeing here is that the two lines cross each other. Now, does that mean that this is a consistent system or an inconsistent? Consistent. All right, so it's consistent. Dependent or independent? Independent. Consistent, independent. Great. Let's take a look at another problem. Problem number 30. Part of the nice thing about this is that it gives you a refresher on graphing. Nothing wrong with that. In fact, at some point I'm going to have you graph one of these equations. Let's take a look at the equations in problem number 30. So those would be y equals negative 1/2 x minus 3 and x plus 2y equals 2. So I'll work on graphing this one. What I want you to do is graph this one. Now you can graph it by any means that you want. I think most of you will probably do a little t-table. That's what I'm going to demonstrate up here, x and y. But graph that any means that you want. I'll walk around and try and help out. Okay, looking pretty good here to start with. A lot of you set x equal to 0 and then set y equals 0. If we set x equals 0, we get 2y equals 2. So what does y equal? 1. If we set y equals 0, 2 times 0 disappears. You're just left with x equals 2. So that's a couple quick points. 0, 1 and 2, 0. And we'll play connect the dots through here. Let's work on graphing the other line then. So for the other line, because you've got y already solved for, we can kind of take advantage of that. I would choose some easy values for x to plug in for y. So an easy value for x would be, say, 0. And another easy value would be, say, 2. Now, why am I choosing 2 as opposed to, well, most people choose 1? What's the benefit of choosing, 2 and the 2 we're going to cancel. Any even number that you put in here is going to cancel out that denominator, and you're going to get an easier point to graph. So 0 and -3, 2 and -4. Those would be a couple more points that you can get out of this. Now, that's not the only way that you can graph this. Let's think about this in terms of what we covered in the last exam. What's the slope of this line, and what's the y-intercept? James, what would be the slope, please? Good. -1/2, and the y-intercept? -3. Slope was what over what? And I'm not looking for the y2 minus y1 over x2 minus x1. A little bit more general. Rise over the run. So this is the rise, and that's the run. So if I start out here with -3, and I want to move in accordance with that slope, where do I have to go to move a slope of -1/2? Down 1 over 2. And guess what? I'm exactly at this point, down 1 over 2. So you can graph this by either plotting points, and if you do, I suggest you choose some clever points so that this 2 can cancel here, or you can use the slope and the intercept. Either way. Are you comfortable with the graphing part of this? So let's play connect the dots here. Does this system of equations have a solution? And if so, what is it? It does not. They are parallel. So there's no solution. Does that mean it's consistent or inconsistent? Ying? Inconsistent. Good. Inconsistent. Thank you. Judy, are these lines dependent or independent? Which one? Independent. Good. Independent. They're different lines. Good. So there's no solution. It's an inconsistent, independent system. Nice. So you're not always guaranteed a solution. You could have a solution, or you could have two lines that are parallel. Let's see what else can happen when we're trying to work with and solve systems of equations. So we've seen one thing. What else can happen? Well, let's move up to problem number, let's see, let's try problem number 40. So problem 40 gives us these two equations, x plus 4y, sorry, fix that, x plus 4y equals 4, and 12y equals 12 minus 3x. So those are our two equations here. Now, kind of like the last one, I'm going to graph both of these. I'll do the first one, you can do the second one, x and y. If I set x equal to 0 in this equation, I get 12y equals 12 minus 0, really. So divide both sides by 12, I get y equals 1. 0 and 1. let's find another point. Let's set y equals 0. If I set y equals 0, I get 0 times 12, which is a 0, equals 12 minus 3x. Let me move the 3x to the side. 3x equals 12. So what does x equal? X equals 4. 4 and 0. And that gives me enough information to graph a line. Now hopefully I didn't make a mistake, because if I made a mistake using only 2 points, I'll never find it. That's why on the first exam I asked you to graph using 3 points. But I'm pretty confident with these, since we're finding the intercepts, it's pretty straightforward, that I didn't make a mistake. So there's my graph of the second equation. I need you to graph the first equation. And do likewise. Do what I just did. Find a couple points and plot them. Okay, so when I set x equal to 0, I get 4y equals 4, which means y equals 1. If I set y equal to 0, what do I get for x? 4. And if you notice, 0, 1 and 4, 0, what's happening with those? Getting the same points, right? And when I graph it, I'm going to get the same line. What's that saying about our system of equations? The same line. So that's a third thing that can happen when you're graphing a system of equations. You could get exactly one solution, so that's consistent, independent, and there's your solution, the point where the lines cross. You could have no solution, in which case you still have an independent system, but it's inconsistent because there's no solution. Or the third case is that you have two lines on top of each other. Let's see if we can't describe this. Is it going to be dependent or independent? Dependent. Now here's one that you need to think about for a second. Is this system of equations consistent or is it inconsistent? Consistent. there's an infinite number of solutions. Everything which is a solution to one equation is a solution to the other equation. So it's dependent and consistent. So those are the three things that can happen when you're trying to solve a system of equations. Now, let's move on down to problem number 50. Oh, by the way, you could actually have seen this ahead of time if you put these in slope-intercept form. Let's see what I mean here. X plus 4y equals 4. If I move the x to the other side, I get 4y equals negative x plus 4. What do I have to do to finish putting this in slope-intercept form? Divide by 4. Y equals negative 1/4 x plus 1. All right, so that's one equation. Let's do the same thing over here with 12y, and I'm going to just change the order here. I'm going to write 12y equals negative 3x plus 12. 12y equals negative 3x plus 12. If I divide everything through by 12, what do I get? I get y equals negative 1/4, right, in lowest terms, plus 1. So is it a surprise that we got a dependent system? Not really, because if you look at those two equations, they're essentially the same. They are identical. So that's why we got the result we did in problem 40. How's that going to apply to other problems? Does it help us out? Well, you can at least get some insight. Problem number 50. Oops. Let's give me a minus there. Minus 3. In problem number 50, before I try and graph this, can you tell me whether or not there's going to be a solution? Let's think of it this way. In what case wouldn't there be a solution? What has to happen for there not to be a solution to this system of equations? They have to be parallel. So the question is, are these lines parallel? Brian, what do you think? Are these lines parallel? No. You can see that here. The slope of this line is 1. The slope of this line is negative 2. Unless those two slopes are the same, they're going to cross. The only time they don't cross is if the slopes are the same. Let's graph these. The easy thing to do, especially because you've got y by itself, is just to plug in some values for x. I'll plug in x equals 0. I get y equals 3. And let's keep it easy. X equals 1. Y equals 4. And so I get some easy points to plot there. So 0, 3, and 1 and 4. And we'll play connect the dots and draw our graph. Not perfect. Close enough. How about the next one? I need some more points here. You don't always have to choose positive values for x. You could choose a negative value. What would be a negative value that I could choose for x? Negative 1? Sure. If I choose negative 1 for x, let's see what that gives me for y. It's going to be y equals negative 2 times negative 1 minus 3. So I get negative 1 and negative 1. I strongly suggest that you not blow off this part of the homework this weekend. And walking around, I see a lot of you struggling graphing these things. This is stuff that we've already covered. And if you're struggling with it, then you need to get better at it. The only way that's going to happen is with practice. So negative 1 and negative 1, and then 0 and negative 3. So we've already got this line graphed. Let's graph this line. Let's see what we get. Okay. And I can see my lines aren't perfect, which is annoying because we need to try and figure out the solution here. If you had to guess at it, roughly speaking, maybe your graph is better than mine. Where do these lines kind of look like they cross each other if they crossed at a nice integer set of points? Yeah, right here, -2, +1. Now, how could I prove that? If I was looking at that going, you know, Jeff, that graph is really pretty crappy. How would you prove it? Yeah, plug it in. Plug it into both here. Here's your x and here's your y. -2 plus 3 is 1. So it checks in this equation. -2 times -2 is 4. And 4 minus 3, again, is 1. So it checks. And it kind of illustrates a problem that you're going to run into in working with the graphs of these types of equations to find a solution. That problem gets worse in number 48, which would be kind of our last one here for this section. Before we do problem 48, is there any wrap-up thoughts on problem 50 here? Please. Oh, absolutely. In fact, after this next problem, we're going to start moving into sections 4.2 and 4.3. Those are going to show us other techniques by which we can solve a system of equations. I think problem number 40 is 48 is going to show you that we really don't want to graph these things to solve it. The reason I discuss graphing is because A, it's good to practice graphing lines. B, I need you to understand some vocabulary: dependent, independent, consistent, inconsistent, etc. So, you know, you're just getting the background information on solving system equations. In practice, we don't solve them by graphing. I mean, we got tons of different techniques to solve them. Graphing is the last thing we're going to do. Yes, ma'am. I'm sorry, couldn't quite hear that. No. 0, I graphed 1 and 4, which should be up here. But I appreciate you checking me, though. Thank you. So I graphed the point 0, 3, which is right here, and the point 1, 4, which is up here. So 1, 4 is right there. So those are those 2 points. And then for the second equation, 0, -3 is down here, and 1, -1 is here. So, okay. That's all right. I appreciate you checking me, though. I really do. Let's finish up with problem number 48. We've got 2 equations. One is x minus 3y equals -2. The other one is 5x plus y equals 10. Now 5x plus y equals 10 is already graphed for us here. So 5x plus y equals 10. What you have to do is graph this equation here. Figure out some x and y values that you can use here to plot this equation and try and estimate the solution. Now I emphasize estimate. It's going to be tough with this one. Unless you draw a really, really good line, it's going to be tough. But it's worth the practice to try and come up with this equation, its graph, etc. Give it a shot. See what you can do. If you're just plotting the intercepts, one of the intercepts you're going to get is just not going to work out nice and even. You're going to get a fraction. And that's okay. That's all right. This stuff that has to be. Oh, 2/3 is fine. Two thirds. I mean, it's not bad. You might be able to find something that works out even. Okay, so let's see here. Most of us probably set x equal to 0. And if you set x equal to 0, we get 0 minus 3y equals negative 2. So that's negative 3y equals negative 2. Negative 2 divided by negative 3 is positive 2/3. The negatives cancel each other out. So positive 2/3, fine. If I set y equal to 0, our work is a little bit easier. Setting y equal to 0, I get x minus 3 times 0 equals negative 2, or basically x equals negative 2. So negative 2 here. 2/3 is about, I don't know, let's see. Yeah, 0.667, so around here. Not to try and be too crazy about it. But let's play connect the dots here and see what we can come up with. So running that through both of these points. Is this system of equations consistent or inconsistent? Consistent. Dependent or independent? Independent. So it's consistent and independent. Let's see if we can't estimate our solution. So let me draw ourselves a little bit of a line here down to the x-axis. And then one over to the y-axis as well. So it looks like for x you're getting about 1.75, and for y you're getting about 1.25. Wow. Can you see a drawback with trying to graph equations to find a solution? I mean, that's tough. I mean, unless your graph is really good, you're not going to be able to find these things. So what we need is a better method to solve our system of equations, because that, what we got now is just not going to work for us too well. Now, in wrapping this thing up, let me recap the big things that you should get. First of all, you should understand what the solution to a system of equations represents. That's where the two lines cross each other, and if there's a solution, it's a consistent system of equation. You should also understand that there's more than this nice case of things that can happen. This is the consistent independent case where you've got exactly one solution. But there's other things. You can end up with no solutions, or you could have an infinite number of solutions. So there's different things that can happen when you're graphing systems of equations. We're not going to pay attention to the graph all that often. A lot of times we're just going to solve our system of equations and either conclude that, yeah, there is a point, and here it is, or conclude that, no, there isn't a point because the lines are the same or the lines are parallel. But we're not often going to actually look at the graph anymore. So for homework, try 13 through 19. Let's see. Homework, section 4.1. 13 through 19. 25 through 29. 33 and 37.